Did you know that this diagram holds the secret to transforming everyday steel items from paper clips to skyscrapers? The Iron-Iron Carbide phase diagram is like a map for material scientists and metallurgists. It shows how steels and cast iron are formed and behave depending on the carbon content and temperature. Understanding the Iron-Iron Carbide phase diagram, including its phases and their related properties, isn't only useful but also crucial, as it forms the basis for understanding the behavior of all steel and cast iron materials. It helps us predict the microstructure of these alloys, which directly affects their properties. In 22 minutes, we will explain this diagram in detail, so stay tuned until the end for a better understanding. Welcome to the channel. What is the Iron-Iron Carbide phase diagram? The Iron-Iron Carbide phase diagram, often simply referred to as the iron-carbon phase diagram, is a diagram with the X and Y axes, where the Y-axis represents temperature and the X-axis represents composition. The diagram is the graphical representation of the phases present in the iron-carbon alloy at different conditions of temperature and carbon composition. It also describes the suitable conditions for two or more phases to exist in equilibrium and how the properties of steels can be radically changed by heat treatment. Steps to draw the Iron-Iron Carbide phase diagram. Step 1. Draw the X-axis and Y-axis, with the X-axis representing the percentage weight of carbon and the Y-axis representing temperature. Step 2. Label temperatures from 0 to 1600 degrees Celsius and carbon weight percentages from 0 to 6.67%. Step 3. Identify the following key temperatures on the Y-axis. 727 degrees Celsius. The eutectoid temperature and the maximum solubility of alpha ferrite. 912 degrees Celsius. The start of austenite formation in pure iron. 1148 degrees Celsius. The eutectic temperature, also marking maximum austenite solubility. 1394 degrees Celsius. The formation of delta ferrite at high temperature. 1493 degrees Celsius. The temperature at which the peritectic transformation occurs. 1538 degrees Celsius. The melting temperature of pure iron. Step 4. Identify key carbon compositions on the X-axis. 0.022%. Maximum solubility of carbon in alpha ferrite and start of the eutectoid line. 0.09%. Maximum solubility of carbon in delta ferrite and start of the peritectic line. 0.18%. Carbon content at the peritectic reaction. 0.55%. Carbon content where the peritectic reaction stops. 0.76%. Carbon content at the eutectoid reaction. 2.14%. Maximum carbon content of steel and start of the eutectic line. 4.3%. Carbon percentage for eutectic reaction. Step 5. Draw the three invariant or horizontal reaction lines, indicating isothermal reactions upon cooling or heating. 1. Peritectic line. From 0.09% to 0.55% at 1493 degrees Celsius. Marking the peritectic reaction point at 0.18% with a dot. 2. Eutectic line. From 2.14% to 6.67% at 1148 degrees Celsius. Marking the eutectic point at 4.3% with a dot. 3. Eutectoid line. From 0.022% to 6.67% at 727 degrees Celsius, with the eutectoid point indicated at 0.76% with a dot. Step 6. Draw the melting curve starting from 1538 degrees Celsius of pure iron, descending to the end of the peritectic line at 0.55% carbon, then to 4.3% at 1148 degrees Celsius of eutectic point, and ascending to 6.67% at 1320 degrees Celsius, This illustrates how the melting point decreases with increasing carbon content up to 4.3%, after which it increases. Step 7. Draw the various austenitic boundaries on the phase diagram. Step 8. Draw the boundary lines for alpha ferrite on the diagram, followed by the delta ferrite boundaries. Finally, label the phase diagram. From 0.005% to 2.14% carbon content, the iron-carbon alloy is classified as steel. Within this range, different grades exist which include low carbon or mild steel, 0.05% to 0.30%. Medium carbon steel, 0.30% to 0.60%. High carbon steel, 0.6% and above. When the carbon content exceeds 2.14%, the material category shifts to cast iron. Cast iron is very hard, but its brittleness significantly limits its applications and manufacturing methods. Identifying the phases and metastable phase in the diagram. The boundary where they intersect marks a specific region on the Iron-Iron Carbide diagram. These regions are phase fields, indicating which phases are present at a given composition and temperature of the alloy. A phase is a chemically and physically distinct region in any phase diagram. Different phases appear in the Iron-Iron Carbide diagram both as single-phase and double-phase regions. The single-phase regions in the diagram include 1. Liquid phase. Marked as L in the diagram, visible in the upper region. As the name suggests, it is a liquid solution of carbon in iron. Pure iron melts at 1538 degrees Celsius. The melting temperature decreases with increasing carbon content up to 4.3%, then rises again with further carbon addition. Alpha ferrite phase. The small triangular region at the bottom left in the diagram is called alpha ferrite. It is a solid solution of carbon in alpha iron, dissolving only 0.008% carbon at room temperature, with a maximum solubility of 0.022% at 727 degrees Celsius. Alpha ferrite has a body-centered cubic crystal structure and is stable below 912 degrees Celsius. 3. Delta ferrite phase. Located at the top left corner, this phase is a solid solution of carbon in delta iron. It has a similar structure to alpha ferrite but exists at high temperatures. The maximum solubility of carbon in delta ferrite is 0.09% at 1493 degrees Celsius, the temperature of the peritectic transformation. Its melting point is 1538 degrees Celsius. 4. Austenite phase. Austenite is an interstitial solid solution of carbon in gamma iron, stable between 912 degrees Celsius and 1394 degrees Celsius. Also known as the gamma phase, it does not exist below 727 degrees Celsius, where the maximum carbon content is about 0.76%, approximately 0.8%. It has a face-centered cubic crystal structure, allowing for high solubility of carbon, up to 2.14% at 1148 degrees Celsius. The densely packed face-centered cubic structure contains fewer, larger vacancies that can accommodate atoms up to 41% of the size of iron without stress. This explains why the maximum solubility of carbon in austenite, 2.14%, exceeds that in ferrite, 0.022%. This phase is non-magnetic. 5. Cementite phase. Cementite, Fe-Fe₃C, is an intermetallic compound of iron and carbon, characterized by high strength and hardness but low toughness. It is the hardest structure on the diagram, making it suitable for strengthening steel. A carbon content of 6.67% corresponds to 100% cementite. While not a true chemical compound, it is an interstitial phase, present at all temperatures with an orthorhombic crystal structure. Its mechanical properties depend on its microstructure, which varies with how it is mixed with ferrite. It decomposes very slowly at room temperature into iron and carbon. Additionally, there are combinations of two phases. Not only single phase exist on the diagram, there is always a double-phase region comprising two phases. These two-phase regions are labeled as 1-to-1. In the area between delta iron and austenite, both phases must be present. Similarly, between austenite and alpha iron, both phases coexist. Above the liquidus line, molten iron exists, so in the phase between liquid iron and delta iron, both molten iron and delta iron are present. Likewise, between molten iron and austenite, both phases are present. Other double-phase fields include molten iron and cementite, gamma solid solution and cementite, and alpha iron solid solution and cementite. Additional phases in the diagram include perlite and ladeburite. Perlite, an eutectoid mixture of ferrite and cementite, forms at 727 degrees Celsius with 0.76% carbon on very slow cooling. It appears as a fine lamella or plate-like mixture, creating a mother-of-pearl pattern under a microscope, from which it derives its name. This phase offers a good balance of strength and ductility, making it suitable for various structural uses. Ladeburite. Ladeburite is an eutectic mixture of austenite and cementite, containing exactly 4.3% carbon. It forms at 1148 degrees Celsius during the cooling of molten cast iron and high-carbon steel. Due to its hardness, it is valued for wear resistance but has poor machinability. Ladeburite is commonly found in white cast iron and high-carbon tool steels, appearing as white intergranular networks under the microscope. The invariant reaction and point on the iron-iron carbide phase diagram. The important part of the iron-iron carbide phase diagram is the invariant points which are present there. The invariant points indicate that they exist at specific compositions and temperatures, and they will not be found at any other points on the phase diagram. These points mark the exact intersections and conditions where three phases coexist stably. As we all know, every invariant reaction in a binary phase diagram is always represented by a horizontal line. In the iron-iron carbide phase diagram, there are three invariant points which are the eutectoid point, eutectic point, and peritectic point. Eutectoid point and reaction. The eutectoid reaction occurs at 0.76% weight carbon at around 727 degrees Celsius. At this point, one solid phase transforms into two other solid phases. That is, austenite transforms into alpha ferrite and cementite upon cooling. This eutectoid structure is called perlite. Eutectic point and reaction. In the eutectic reaction, the liquid transforms into two solid phases. That is, liquid iron changes into austenite and cementite. This reaction occurs at 1148 degrees Celsius at a composition of 4.3% weight of carbon. Peritectic point and reaction. In the peritectic reaction, the liquid and a solid phase transform into a second solid phase. That is, liquid iron plus delta iron transform into austenite or gamma iron. This reaction takes place at a temperature of 1493 degrees Celsius, and exactly at a composition of 0.18% carbon. Hypoeutectoid and Hypereutectoid steel. Hypoeutectoid steel. Compositions to the left of the eutectoid point, 0.022 to 0.76 weight% of carbon, are called hypoeutectoid steels. Hypo means less than. So, steels with less than 0.76% carbon are classified as hypoeutectoid steels. These consist of primary proeutectoid alpha ferrite and perlite. Proeutectoid alpha ferrite already exists in the microstructure before the eutectoid temperature, which is 727 degrees Celsius. During the cooling of a typical hypoeutectoid alloy from the austenite phase, it enters a region where the stable phases are ferrite and austenite. The alpha ferrite nucleates and grows within the phase, leaving the remaining austenite richer in carbon. At 727 degrees Celsius, the remaining austenite reaches the eutectoid composition, and further cooling transforms it into perlite. As a result, the microstructure will contain both perlite and proeutectoid ferrite. Hypoeutectoid steel. Compositions to the right of the eutectoid point, 0.76% to 2.14 weight% of carbon, are called hypoeutectoid steels, which are greater than the eutectoid composition. Hypoeutectoid steels contain primary proeutectoid cementite and perlite. The presence of proeutectoid cementite indicates that cementite already exists before the transformation, before reaching the eutectoid temperature. In the microstructure, you will see both proeutectoid cementite and perlite phases. Hypoeutectic and hypoeutectic alloys. Alloys with compositions less than the eutectic composition are termed hypoeutectic alloys, while those with higher compositions are called hypoeutectic alloys. Critical temperatures. In the Iron-Iron Carbide phase diagram, the critical temperature refers to specific phase transformation points where the microstructure of steel and cast iron changes. Different critical temperatures in the Iron-Iron Carbide phase diagram are crucial for both theoretical understanding and practical applications. These critical temperatures are often referenced when discussing steel heat treatment and the phase transformations that occur during heating and cooling. Multiple lines are visible in the diagram, labeled A1, A2, A3, A4, and ACM. The A in their name stands for the word arrest. Typically, when heating an alloy, its temperature increases. However, along these lines, A1, A2, A3, A4, and ACM, the heating results in a realignment of the structures into a different phase, and the temperature remains constant until the phase change is complete. This is known as thermal arrest, as the temperature stays steady. Line A1. Lower critical temperature A1. This is the eutectoid temperature line. It marks where austenite begins to transform into perlite, a mixture of alpha ferrite and cementite, during cooling. It occurs at 727 degrees Celsius in the diagram and is the same for all steel compositions. Below this temperature, austenite does not exist. Line A3. Line A3 indicates the temperature below which ferrite begins to form as a result of ejection from austenite during cooling in hypoeutectoid alloys. It can also refer to the temperature at which ferrite starts to transform into austenite during heating. This line is known as the upper critical temperature for hypoeutectoid steels. It forms the boundary with the gamma phase, and its temperature varies with carbon content, decreasing from 910 degrees Celsius for pure iron to 727 degrees Celsius at the eutectoid composition, 0.77% carbon. Line ACM. The upper critical temperature line ACM is the temperature below which cementite begins to form due to ejection from austenite in hypoeutectoid alloys. It can also refer to the temperature at which cementite starts transforming into austenite during heating. This is the upper critical temperature for hypoeutectoid steels. It varies with carbon content, decreasing from 1148 degrees Celsius at about 2.14% carbon to 727 degrees Celsius at the eutectoid composition of 0.77% carbon. Line A2. This line is known as the Curie temperature of ferrite, at which ferromagnetic ferrite becomes paramagnetic. It occurs at 769 degrees Celsius. This is the temperature where iron loses its magnetic properties, changing from ferromagnetic to paramagnetic, without undergoing a structural phase change. Line A0. This indicates the temperature at which cementite changes from ferromagnetic to paramagnetic. It is known as the Curie temperature of cementite, at 210 degrees Celsius. Line A4. This line marks the completion of the transformation from austenite to delta ferrite. The transformation occurs at 1394 degrees Celsius in pure iron but increases with additional carbon. To understand the transformation processes, consider a steel with a eutectoid composition of 0.76% carbon being slowly cooled along B1 to B2. At the higher temperature, only austenite is present, with 0.76% carbon dissolved in solid solution within the Fe-Fe₃C structure. When the steel cools through 727 degrees Celsius, several changes occur simultaneously. The iron tends to change its crystal structure from Fe₃C austenite to BCC ferrite, but the ferrite can only contain 0.022% carbon in solid solution. The excess carbon is rejected and forms the carbon-rich intermetallic known as cementite. The net reaction at the eutectoid involves the formation of a perlite structure, since the chemical separation occurs entirely within solid crystal structures. The resulting structure is a fine mixture of ferrite and cementite. Effects of alloying elements on the iron-iron carbide phase diagram. Adding more alloying elements alters the temperature composition relationship shown on the phase diagram. In the iron-iron carbide phase diagram, carbon is the most significant alloying element added to iron regarding the primary phases that form. However, the shape and position of the phase fields on the diagram will change when alloying elements such as magnesium, chromium, and nickel are introduced. Even for alloys containing more than 3 alloying elements, binary phase diagrams often provide a useful general understanding of the primary phases in relation to the key alloying element. In conclusion, when using a phase diagram, it is crucial to understand that the relationship between phases, alloy composition, and temperature is based on conditions of slow heating and cooling. Slow heating and cooling enable atoms within the metal to move freely, allowing the system to reach equilibrium. However, many heat treating and solidification processes involve rapid heating and cooling. Under these circumstances, phases may be absent or present differently, compared to the predictions of the phase diagram. Therefore, it is important to understand the kinetics of phase transformations. That is, how temperature, time, cooling rate, and heating rate influence phase changes within an alloy. The phase diagram does not provide this kinetic information. Regarding martensite, it is not an equilibrium phase in carbon, low alloy, and tool steels. Steel must be heated to form austenite and then cooled very quickly to produce martensite. This process is not equilibrium-based, which is why martensite does not appear on the iron-carbon phase diagram. If you found this video helpful, please like and share the video, subscribe to the channel and turn on the notification bell for more content. Thank you for watching and see you in the next video. Goodbye.